or there should be a session for taking pictures?
Yes, sir. Maybe after the class.
No, I think before the lecture.
Oh,
It's
before.
better
Okay.
before the lecture. So everybody is still there. Okay?
Okay, sir.
I'm afraid if after the lecture there will be, only just a few that still join in the meeting. Okay?
Okay.
Yeah. Maybe I will ask Professor Jeff to hold a second for us to take pictures, right?
Yes.
Yeah. All right. Rifki, can I find Rifki here?
Ya, Prof. Siap.
Okay, I found Rashid. And as I told you, there will be a screenshot for this lecture. So before the lecture starts, I guess it's better to have a screenshot session, right? Rifki, can you hear me?
Ya, Prof. Baik, Prof.
So, are you already as a co-host? Not yet. Seems to me you not yet. Yes.
Saya sudah jadi coach, Prof.
Speak English, please. Sid.
Saya sudah jadi co-host juga, Prof.
Speak English, please.
Okay. I have become the co-host, sir.
Okay. Okay, I think because we still have another 14 minutes, I will be a host for this session, okay? But after screenshot session, I will leave to Professor Jeff to lead the meeting or the lecture, okay? And I think up until 4 o'clock, right? It's because this is a 3-hour session, so it starts around 1:30 to 4 o'clock, okay? And before we start, Buidi will also be here to give a welcoming speech to Professor Jeff, because this is a project, okay? This is a project from the department, okay? This is not an individual webinar that usually the laboratory holds once in a month or once in 2 months. So we are happy to have Buidi here. Okay, just give a welcoming speech to us and to Professor Jeff. Okay, and I hope some of you maybe will have a chance to study for master degree at National Taiwan University. Okay, because it's #1 university, ranking #1 in Taiwan. Okay, so from IPS, there is not so many graduate students from IPS, studying at NTU. So I hope some of you will be able to take a master degree program at NTU. Okay, other than that, I don't know about the attendance. Okay, for you, for example, Eki and Rashid, you are in the different class, right? So
Right, sir.
yeah, so how you will get the attendance list for this session?
As I know, Mr. Rendra will give it in my test classroom.
Okay, so he will open for the attendance list for the class, Pak Rendra,
Yes,
do you think? Okay.
he will
So,
give code presentation code.
I
Maybe.
see. Okay, okay. Make sure it's also true for Pak Hakun's class. Okay? Pak Hakun or Pak Anas class. Alright? However, do we make a form to attend this lecture through Google? Vicky?
Yes, sir.
Yeah, did you make a form of attendance by
Okay.
using Google format?
Not yet, but I will try to make it now, sir.
Okay, yeah, put it in the chat room. Okay? So
Okay, sir.
everyone can do that. Yeah. Alright, let me see. Waiting. Oh, by the way, for everyone, Amanda, Marcel, did you get the material? I think I gave to you or I gave to Ricky to distribute it. How's it? Did you get the material?
Yes, I get the material, sir.
Yeah, but how about Marcel and
Not yet, sir.
how come? Vicky? Vicky?
Yes, yes, sir.
Maybe you'd better also put the file for the material in the chat room
Okay, sir.
for the heat integration.
Okay, sir.
Well, the heat integration and the book.
Okay, sir. I will do it.
Yeah, so
Hi, Renato.
hi, how are you, Jeff?
Good. How are you?
Fine. Yeah,
Good to see you again.
yeah, nice to see you again. I have Dr. Vidya Stuti. She's the head of the department. She said she will join us around 1:30. Can we wait for her for a little bit? Maybe it takes.
Of course. You mean? Oh, yeah, 1:30 your time. Sure. No problem. We're still early. I have time. In
Yeah.
fact, when when I teach this lecture at NTU, it's a 2-hour lecture.
Oh, I see.
So I think
No problem. No problem.
we may end a little bit early, or we can start late. We have
Yes.
flexibility.
Okay.
And when I do it at NTU, if you look at the lecture notes, there's 2 examples. And the first one, I lead the students through it in great detail, showing every step of the heat integration.
Mhm.
And then in the second part, I'll let the students work on the example.
Uh-huh.
And we'll see if they can get through the first part, and then we'll come back together and talk about the first part, and then they can work on the second part. And
Yeah. Do you think the students will have enough time to do that?
yes,
Okay, good.
I hope
Yeah.
so.
Because when we talk about the heat integration, especially when we do for the pairing between hot stream and cold stream, it's a little bit, take time for that to get
Well,
it right.
the examples that I have are quite simple. They're
Oh, I see. Okay.
they're tutorial examples. There's only 2 or 3 hot streams and 2 or 3 cold streams.
Mhm. Do you teach also about using a grid diagram in order to pair which hot stream with which cold stream? Because
Grid
you
diagram.
cannot.
I'm not sure.
Yeah.
I'm not sure what a grid diagram is.
Okay. The problem is we use the Robin Smith's book.
Okay.
Chemical process design and simulation and integration. In there, he talked much about heat integration and using grid diagram. Okay, how to pair between hot streams and cold streams.
Okay. I have to look at that book and see what he means by a grid diagram. Maybe I have something similar, but I just have a different name. I don't know.
Okay.
Well-
Yeah. That's right.
I don't know.
Yeah.
Are you guys still all online with your courses?
Well, actually, this is the time for me to teach the course. However, now I gave it to you. So.
Of course. But I mean, does the university require only online courses? Are you allowed to meet on campus with the coronavirus?
With coronavirus, it's just for new students, not for the students.
Mm-hmm.
Yeah. So it's just for the freshmen, not for the second year, third year, or fourth year. For the moment, for the offline course.
I see.
Yeah. How about in Taiwan?
We're doing better. We
I think so.
we had the coronavirus under control, and then in May of this year, there was an outbreak, and we had to shut everything down.
Mm-hmm.
And now I just got an email today that says we're allowed to resume in-person courses next week.
I see. Mm-hmm.
So fingers crossed that we can get back to normal here.
Yeah. Well, very good.
We're a little bit lucky since Taiwan is kind of a smaller island. I think it's a little bit easier to control things than in a larger country.
Yeah, that's right. Yeah, it's going to be difficult for Indonesia because we have so many
Things are very difficult in the United States still.
Yeah.
even though we have a lot of vaccine, it's still very difficult in the United States. It's very frustrating.
Yeah. That's right.
Oh, I see.
So, for your lecture, we will have two assistants for you. One is Mr. Marcel, the other one is Miss Amanda. They are co-hosts.
Okay, wonderful. Thank you both.
Welcome, sir.
Right, and let me see.
So if there's a technical problem, if you can't hear me or you can't see my screen or I'm doing something that's obviously not the right thing to do, just let me know.
All right, sir.
I'm still kind of a novice with this online synchronous teaching over the internet.
But you don't have any problem with the internet for, doing online?
The connection quality is fine. The problem is my technical ability is not so good. So I might choose the wrong setting in the software. Everyone, there's so many different software programs. All these software programs suddenly appeared during the pandemic. There's Zoom and Cisco WebEx and Microsoft Teams and I think I'm already starting to get old. Younger people can figure out all this software very quickly, but I'm still one step behind. So I need to rely on smart young people to keep me on top of things.
Yeah. But I'm going to retire within 1 or 2 years from now.
Oh, congratulations.
Yeah, thank you.
Any plans for retirement?
Not yet. Yeah. So let me see. I think I see Dr. Vidya Stutia, my head of department.
Good afternoon.
Good afternoon.
Hello.
Viti.
Professor Renanto and Professor Jeff.
Hello.
Yeah.
Hello. Nice to meet you today.
Nice to meet you also. Thank you for joining us.
You're welcome.
Yeah. Go Viti, as you already are in the meeting room here. Can we start, or is there anyone else? Viti from the
Yes,
department?
please, Prof. Renanto, to continue the. You can start this webinar, please.
Okay. Before we are going to the seminar, maybe do you want to give a welcoming speech first?
Okay. Thank you. Good afternoon, everybody. Let us give a warm welcome to Prof. Jeffrey D. Ward from National Taiwan University as a guest lecturer about heat integration. I would like to express my appreciation and thanks to Prof. Jeffrey, who will share the knowledge about heat integration. Yeah, we hope this guest lecture will help our students to understand more deeply about heat integration from Professor Jeffrey. So therefore, please pay attention, listen carefully, and after that, please, every student can give a question related about the lecture.
Yes.
Furthermore, I also hope we can collaborate between ITS and NTU that can be continued. For example, about student exchange or research collaboration. I hope we can, for example, double degree. We have we also want to have a collaboration like that. Okay, I think enough for my welcome speech. I should give to the time for Professor Renanto as a moderator of this guest lecture today. Thank you.
Thank you, Bu Wide. Thank you very much for the welcoming speech. Now, before we start with the lecture, I would like to have a screenshot picture of the audience first. So, Amanda, can you start that? Can you start with that, Amanda?
Yes, sir. Maybe
Okay.
first screen. Wait. Okay. Okay. 1, 2, 3. Okay. Wait. The second screen. 3, 2, 1. Okay.
You have so many enthusiastic students.
I'm sorry. They like to, they want to to see and to hear your lecture. To listen to your lecture.
Thank you.
Third screen. 3, 2, 1. Okay. Last screen. 3, 2, 1. Okay, done, sir. Thank you.
Thank you. Thank you very much. Okay, Professor Jeff, I think it's about time. You can start with your lecture. All the time is yours now. You can, arrange them like the one before when you gave lecture here. Okay, maybe each 50 minutes you want to have a break for 5 or 10 minutes. It's okay. Do whatever you want. Okay.
Okay.
I will leave it to you. Thank you.
Okay, thank you. I will share my screen. And go into full screen mode, hopefully. Okay, does everyone see the full screen?
Yes, sir.
And me. Okay, very good. Thank you, Renando, for this kind invitation to share with your students a lecture about heat integration, which I typically give in our junior level process design theory course. So
Please, sir. Please, sir. Before we start, I would like to. Is it okay for us to record this program?
Yes, you may.
All right. Thank you, sir.
Of course. So
recording in progress.
This meeting is being recorded. Got it. Okay. Oops, I lost my full screen. Okay, still on full screen. Still doing good. Okay. So the basic idea, heat integration, is typically taught as a component of chemical process design, as an item in the curriculum in a process design course. And the basic idea is that if you are designing a chemical process, if you have developed a basic flow sheet for a chemical process, perhaps with some reaction, some raw materials entering, some reaction, perhaps some separation, and perhaps some recycle, if you look at the flow sheet, you'll find that there are a number of points in the flow sheet where the temperature or the phase of a stream needs to be changed. We need to heat a stream or vaporize a stream or cool a stream or condense a stream. For example, a chemical reaction might take place at a very high temperature, and so we need to heat the feed to the reactor, and then after that, separation might take place at a lower temperature, and so we need to cool the reactor effluent. Okay, almost always when we're dealing with chemical process design, we have available to us what we call utilities that we can use for heating and cooling. Utilities refer to things that are produced in a centralized location and then distributed to many users on demand. Can you guys admit, just go ahead and admit anyone that's coming in if you can. That's perfect. Thank you. So examples of utilities include electricity, steam for heating, cooling water, natural gas. In your home or dormitory or apartment, we sometimes consider telephone service, internet access, cable television to be utilities. They're produced at a central location and then they are distributed to many users on demand. So in our process design, we have available utilities for heating and cooling. But if we always use the utilities for heating and cooling, we will end up consuming more energy than necessary. It would be wasteful to always use steam or natural gas furnace for heating and then to use cooling water for cooling. In order to save energy, reduce energy demand, reduce cost, and of course reduce the environmental impact, carbon emissions, and other pollution, we can attempt to implement what we call process-to-process heat exchange. If I have one stream that's cold and I need to heat it, and I have another stream that's hot and I need to cool it, rather than using the utilities, I can try to design a heat exchanger that directly transfers energy between the two process streams. Okay, when I'm doing that, I need to have some insight from fundamental chemical engineering principles. In particular, the most important fundamental chemical principles for heat exchanger network design are the first and second law of thermodynamics. Okay, you'll remember from a thermodynamics class, the first law of thermodynamics tells us that energy is conserved. And the second law of thermodynamics tells us that the entropy of a closed system can only increase. The practical implication of the second law of thermodynamics for heat exchanger design is that I can only transfer heat from a hot stream to a cold stream. If I place a hot object in contact with a cold object, energy will transfer spontaneously from the hot object to the cold object, but never from the cold object to the hot object. So as I am designing my heat exchanger network, I need to keep in mind that energy is going to be conserved. So all of the energy lost by the hot stream is going to be absorbed by the cold stream, and that heat transfer will only occur will always occur in the direction from the hot stream to the cold stream. I can't transfer energy against the temperature driving force without a much more complicated operation like a heat pump. Okay, we should also be aware when we're designing a heat exchanger network that we will encounter a trade-off between capital cost, process flexibility and operability, and energy savings. Okay, you might naively think that we should always try to recover absolutely as much energy as we possibly can with the heat exchanger network. This is not the case. If you attempt to do that, if you attempt to recover every possible watt or joule of energy or power, you'll end up with a heat exchanger network that consists of too many extremely large heat exchangers. And there are costs associated with purchasing the heat exchangers, and there's also an environmental impact associated with manufacturing the heat exchangers. So we're seeking a trade-off between capital and operating cost. The more energy we try to recover, the more heat exchange area we're going to need, the larger capital cost, the larger cost and environmental impact associated with the manufacturing of the heat recovery equipment. So we need to keep this trade-off in mind as we're designing our heat exchanger network. And lastly on this slide, heat integration is a very important topic in chemical engineering. It has been widely studied for many decades, and people have developed a systematic method for designing heat exchanger networks. And we will present in this topic a systematic method for designing heat exchanger networks and illustrate the method using some relatively simple examples. Okay, so our basic procedure for designing a heat exchanger network, there are 5 steps. We'll begin by selecting what we call a minimum approach temperature. The minimum approach temperature is a heuristic value in units of temperature, like centigrade, that tells us the minimum temperature driving force we will accept for our heat exchanger. Okay, remember, energy can only be transferred from a hot stream to a cold stream if the difference in temperature between the hot stream and the cold stream is very small, say only 1 centigrade degree or half a centigrade degree. The driving force would be so small that the heat exchanger would end up having to be impractically large, have tens of thousands or hundreds of thousands of square meters of heat exchange area, which is not practical. So in order to develop a reasonable conceptual design of a heat integration network, we choose what we call a minimum approach temperature. And a common value for the minimum approach temperature would be between, say, 10 and 20 centigrade degrees. So once we've chosen the minimum approach temperature, if we choose 10 centigrade degrees, then we're saying our heat exchangers will be designed so that there is always at least 10 centigrade degrees difference between the hot stream temperature and the cold stream temperature to provide a driving force for energy transfer. Okay, once we've chosen the minimum approach temperature, we then construct what we call a temperature interval diagram. And you'll see what all of these diagrams look like as we work through an example on the next several slides. We construct a temperature interval diagram. We construct a cascade diagram. Then we calculate the minimum number of heat exchangers, and we design the heat exchanger network. Okay, so here is an example of a relatively simple case. We have 6 streams in our process, and they have been identified as being either hot streams or cold streams. Okay, you should be aware, importantly and sometimes confusingly, when we talk about heat integration and we say that a stream is hot or cold, we are actually not referring to the temperature. Instead, what we mean when we say hot or cold is whether the stream needs to be heated or cooled, whether it requires heating or requires cooling. So a hot stream is a stream that requires cooling. It's not necessarily a stream at a very high temperature, but it's a stream that is too hot and we want to make it cooler. We want to remove energy from that stream. Similarly, a cold stream is not necessarily a stream that has a low temperature, but rather it's a stream that needs to be heated up. The stream is too cold. It requires additional energy for heating. Okay, so when we say hot and cold, we're not necessarily talking about the temperature. We're talking about what we want to do with the stream. Hot streams are streams that we want to cool down, and cold streams are streams that we want to heat up. Okay, and in this example, we're choosing a minimum approach temperature of 10 centigrade degrees. Okay, also in this table, for each of my 6 streams, I am listing here the mass flow rate in units of mass per time, kilograms per second, and the mass heat capacity of the stream in kilojoules per kilogram degree centigrade. Okay, so this is the heat capacity of the material that's flowing in the stream, and this is the mass flow rate. If I multiply these two together, I get a combined value, m dot Cp, which we can call the flow capacity of the stream. Okay, and the flow capacity has units of power per degree centigrade, and it indicates how much power, how much energy per time is required to raise the stream temperature by 1 centigrade degree. So if I add 8 kilowatts of power to stream 1 continuously at some point in the stream, then the temperature of that stream will rise by 1 centigrade degree. Okay, that's the mass flow rate times the mass heat capacity, gives the flow capacity in units of power per degree centigrade. Okay, then also here, I'm listing the required inlet temperature and the required outlet temperature from my flow sheet. So based on my process design, I know the temperature of the stream coming in, and I know the temperature that I want the stream to be after it leaves. Okay, and then finally, if I take the difference between the inlet and outlet temperature and I multiply by the flow capacity, I'll get the amount of power that needs to be supplied to this stream. So stream 1 requires 1200 kilowatts of power, 1.2 megawatts of power. Stream 2 requires 200 kilowatts of power. Stream 3 requires 450 kilowatts of power. Stream 4 is a cold stream. Stream 4 has energy available. Stream 4 needs to, I've been speaking imprecisely. These are hot streams and they are supplying energy. So stream 1 has an additional 1.2 megawatts of energy to give up or needs to be removed from the stream. Stream 2 has 200 kilowatts that need to be removed. Stream 3 has 450 kilowatts that need to be removed. Stream 4 is a cold stream. It needs to be heated. Stream 4 requires 500 kilowatts. We need to transfer 500 kilowatts to stream 4, 800 kilowatts to stream 5, and 600 kilowatts to stream 6. Okay, so this table contains all of the information that we need for the design of our heat exchanger network. It's summarized quite concisely in this table. I guess I should pause for a moment at this point and ask if there are any questions so far. If you have any questions, you can always, I think there's a chat feature, or you can raise your hand or just unmute yourself and ask a question. Is everyone okay so far? Understand what we're proposing to do and understand what information is shown in this table? Okay, go ahead.
Oh, no question. Yes. I think it's okay. No question.
Okay, very good. Thank you. Taiwanese students are very shy. I think Indonesian students are not quite so shy. In Taiwan, if I ask that question, everyone will sit completely silently, and then I don't know what to do. So please feel free to interrupt. When I teach this lecture in Taiwan, it's actually only a 2-hour class, so we actually have an extra half an hour here that I can use to answer any questions that anyone has. Okay, so using this information, we can proceed to the next step of our design procedure, which is to construct what we call the temperature interval diagram. And the temperature interval diagram represents the heat integration problem, as the name suggests, in terms of temperature intervals. Okay, in particular, there are 2 sets of temperature intervals, one on the left for the hot streams which need to be cooled, and one on the right for the cold streams which need to be heated. Okay, here again you can see stream 4 is a cold stream. It needs to be heated, but it's actually hotter than stream 2, which is a hot stream that needs to be cooled. So again, when we say hot streams, we mean streams that need to be cooled, and when we say cold streams, we mean streams that need to be heated. So my hot streams are on the left, and my cold streams are on the right. And my temperature intervals are labeled here A, B, C, D. If you follow these horizontal lines here, you'll see on the left that this line is labeled 300 centigrade degrees, and on the right, the same line is labeled 290 centigrade degrees. The difference here is 10 centigrade degrees, which is my minimum approach temperature. Okay, remember that's the minimum temperature that I'm going to permit for heat transfer. So I have shifted, on the right, I have shifted my temperature scale down by 10 degrees. So if I have a cold stream at 290, it can be matched with a hot stream at 300. If this was 300 and 300, if these were the same, then they wouldn't match, because I'm not going to permit heat transfer without 10 centigrade degrees of driving force at least. Okay, so on the left, temperatures go from 300 to 50 degrees centigrade, and on the right, they go from 290 to 40 centigrade degrees. Okay, then going across here, I have my streams 1, 2, 3, 4, 5, 6. And I have also copied over the flow capacity for each stream, 1, 2, 3, 4, 5, 6, from my table. And remember, these have units of power per temperature. Okay, then I'm going to draw, for each stream, I'm going to draw an arrow indicating the inlet temperature and the outlet temperature for that stream. So stream 1 is a hot stream. It's supplied at 300 centigrade degrees, and it needs to be cooled down to 150 degrees centigrade. Stream 2, also a hot stream, is supplied at 150 degrees centigrade and needs to be cooled down to 50 degrees centigrade. And stream 3 from 200 to 50. And my cold streams that need to be heated up, stream 4 is supplied at 190 and needs to be heated to 290. Stream 5 is supplied at 90 and needs to be heated to 190. And stream 6 is supplied at 40 and needs to be heated to 190. Okay, so having drawn the arrows, I can see then where my temperature intervals are going to be. Okay, anytime an arrow has to start and end on a temperature interval line. Okay, so this one goes from 300 to 150. This one goes from 190 to 290. So I'm going to need a line here, and this will be interval A. Then here, stream 3 starts at 200, and stream 5 and stream 6 need to be heated to 190. So this is another horizontal line. I end up with 5 horizontal lines, which result in 4 temperature intervals. Okay, then over here, I'm going to calculate the amount of energy that is available, or the amount of energy that is required in each of my temperature intervals, or more specifically, I should say power, okay, energy per time. So in stream A, I have 2 streams in, I should say temperature interval A. In temperature interval A, I have 2 streams, stream 1 and stream 4. Stream 1 needs to be cooled from 300 all the way down to 150, but in interval A, we'll just consider the region between 300 and 200. And over here, temperature stream 4 needs to be heated from 190 to 290. Stream 1 has a flow capacity of 8 kilowatts per degree centigrade, and it's heated by 100. Needs to be, stream 1 is a hot stream that's going to be cooled. It's going to be cooled from 300 to 200 in this interval. So stream 1 will release 8 times 100. 300 minus 200 is 100. 8 times 100 equals 800 kilowatts. Stream 1 has 800 kilowatts available in temperature interval A. Stream 2 and stream 3 aren't in this interval. Stream 5 needs to be heated from 190 to 290. And its flow capacity is 5 kilowatts per degree centigrade. So stream 4 will require 500 kilowatts of power in interval A. So stream 1 is releasing 800 kilowatts. Stream 4 is consuming 500 kilowatts. That leaves 300 kilowatts of additional power available in temperature interval A. Okay, and the important concept is that because this energy is available at the highest temperature, temperature interval A is the highest temperature, energy available at a high temperature can be passed down to streams at a lower temperature. I can pass energy from interval A to interval B. By contrast, I cannot pass energy up the diagram. I cannot pass energy from interval B back up to interval A, or from C back up to B. That violates the second law of thermodynamics. Okay, but lucky for me, in this example, I have 300 kilowatts of power available in interval A. I can pass those down to interval B if I need them in interval B. So let's look at what's happening in interval B. In interval B now, there are 2 hot streams. Stream 1 in interval B needs to be cooled from 200 to 150 degrees centigrade. And stream 3 also needs to be cooled from 200 to 150 degrees centigrade. Okay, so adding these flow capacities up, 8 plus 3 is 11, and multiplying by 50 gives 550 kilowatts of power available in interval B from stream 1 and stream 3. Stream 1 and stream 3 can provide 550 kilowatts of power. Over here, on the cold stream side, stream 5 needs to be heated from 140 to 190, and stream 6 also needs to be heated from 140 to 190. Stream 5 has a flow capacity of 8, and stream 6 has a flow capacity of 4. So 8 plus 4 is 12. 12 times 50 should be 600. And so in interval B, I have 550 kilowatts available, but I require 600 kilowatts to heat the cold stream. Fortunately for me, I have 300 kilowatts available at a higher temperature. I can pass 50 kilowatts down to interval B without a problem. Okay, so here, this is indicating the amount of energy available at this interval or required at this interval. So in interval A, 300 kilowatts is available. In interval B, 50 kilowatts is demanded. That's okay. I'm still net positive. I still have 250 kilowatts available that I could pass down to interval C if I want to. Okay, continuing on to interval C, now goes from 150 to 100. Now stream 1 is done. I don't need to cool stream 1 anymore. But stream 2 needs to be cooled from 150 to 100, and stream 3 needs to be cooled from 150 to 100. So that's 2 plus 3 is 5, times 50 is 250 kilowatts available from stream 2 and stream 3. Okay, unfortunately over here, now stream 5 and stream 6 require 8 plus 4 is 12 times 50 should be 12 times 50 is 600. Is that right? Yes, 600 and 250 over here. I require 600. I only have 250, and so I have a demand of 350. Okay, now I have a problem. I require 350 kilowatts of energy, but I only have 250 coming down from higher temperatures. So in interval C, I'm going to require some external utility. I'm going to require hot utility. I'm going to need to use steam or a furnace or some other external source of energy in order to meet this requirement here. I don't have enough that I can pass down from a higher temperature. Okay, and lastly, in interval D, stream 2 and 3 need to be cooled from 100 down to 50. And in interval D, only stream 6 needs to be heated from 40 to 90. Here the flow capacity is 5, here the flow capacity is 4. So I actually have 50 kilowatts extra energy in interval D. Okay, unfortunately for me, because of the second law of thermodynamics, I cannot pass this energy up the diagram. Okay, I'm out of luck. There's no way to use this 50 kilowatts to heat a stream in interval C because that would violate the second law of thermodynamics. So I have no choice but to reject this 50 kilowatts to cooling water, to a cold utility. Okay, and then I can add all of these energy demands up, and the sum of all of these numbers is negative 50. This indicates if the second law of thermodynamics was not a consideration, only considering the first law of thermodynamics, only considering the energy available and the energy required, the difference between the energy available and the energy required is 50 kilowatts. So by the first law of thermodynamics, I'm going to need at least 50 kilowatts of heating. And as we'll see later, by the second law of thermodynamics, I'm actually going to need 100 kilowatts of energy, and I'm going to have to reject 50 kilowatts to the cooling water. Okay, how about that? Any questions about this slide? Temperature interval diagram. Still doing good? Later in the lecture, I'm going to give you a second example, and I'm going to ask you to work on it by yourselves. So please do ask questions if you have any questions. Okay, if we are still doing well, then the next thing to do is draw what we call the energy cascade diagram. Okay, this is kind of a summary of what we saw in the temperature interval diagram, but we're going to introduce an additional concept which we call the pinch, which is labeled here. Okay, but at first you can see what we have here. On the left is the hot utility, on the right is the cold utility, And then these blocks labeled A, B, C, and D correspond to the temperature intervals. Okay, and you'll remember from the diagram on the previous slide, in interval A, I have a surplus of 300 kilowatts, which I can pass down to interval B. Okay, so 300 kilowatts available, 300 kilowatts is passed down. In interval B, a net of 50 kilowatts is required. It's negative 50. I'm passing 300 down. I still have 250 available. Then in interval C, 350 kilowatts are required, but I only have 250 kilowatts available. I have no choice but to pass 100 kilowatts from the hot utility. There's no other source of heating at this higher temperature other than a utility. So 100 kilowatts of energy is required here. And the idea of the pinch is that because hot utility is required here and cold utility is required here, it's never a good idea to transfer energy across the pinch point. Okay, as you'll see, we'll show on the next slide, if I were to transfer more than 100 kilowatts to interval C here, if I were to transfer 120 kilowatts here to interval C, and then pass 20 kilowatts down to interval D, I would just have to reject that 20 kilowatts to the cold utility. So essentially, I would be directly connecting the hot utility and the cold utility together, directly wasting energy, which is obviously not a good idea. So we define what we call the pinch point, and it's explained in words on the next slide. The temperature at the top of the highest temperature zone where cooling is required is called the pinch temperature. So in interval D, cooling is required. So this point here, we call the pinch point. Or since there's a 10 centigrade difference between here and here, we might call it the pinch zone. We might say between 90 and 100 centigrade degrees is the pinch zone. Let's skip ahead here. Okay. So the temperature at the top of the highest temperature zone where cooling is required is called the pinch temperature. Heating may be required at multiple points above the pinch temperature, and cooling may be required at multiple points below the pinch temperature, but no cooling is required above the pinch temperature, and no heating is required below the pinch temperature. In this example, the pinch temperature is at 100 degrees C for the hot streams and 90 degrees C for the cold streams, or we could call 90 to 100 degrees C the pinch zone. And to minimize utility consumption, we should not transfer energy across the pinch. In this example, that means no heat exchanger should transfer energy from a hot stream with a temperature above 100 degrees C to a cold stream below 90 degrees C. And you can see why here. If I were to add more than 100 kilowatts here and then pass that energy across the pinch, I would just end up having to reject it to the cold utility. So this power Q here is completely wasted. We're wasting the hot utility and the cold utility. Okay, some cascade diagrams do not have a pinch, and that corresponds to the case where only one utility is required. Sometimes when you conduct the analysis, you find that, for example, here, no hot utility is required. At each temperature interval, more than enough energy is available, and so we only need to use the cold utility. In that case, we say that there's no pinch temperature or no pinch zone. Similarly here, at every stage, no cold utility is required. Every stage requires more energy than it has available, and so we only supply hot utility. Again, there's no pinch in this case. Okay, any questions so far? Everybody still with me? I can't see anyone else's faces, so I don't know if people are following me or not.
Yeah, following.
We're following? Okay. All right. I'm trusting your teaching assistant here. If your teaching assistant is, if you're scared to speak, you can send a message to your teaching assistant and he can pass the message along to me. Okay. Continuing on then, The next step is to determine the minimum number of heat exchangers above the pinch. Okay, and you should be aware this does not necessarily correspond to the final design of the heat exchanger network. We're just going to determine the minimum number of exchangers required above and below the pinch. So I should say, after we identify the pinch temperature, we kind of separate the problem into two parts. Since we know that we're not going to transfer heat across the pinch, we design the heat exchanger networks above and below the pinch separately. Okay, so we will start above the pinch at temperatures higher than the pinch temperature, and we will determine the minimum number of heat exchangers by trying to match hot streams with cold streams in a way that minimizes the number of heat exchangers. Okay, so above the pinch, stream 1 with a heat duty with an energy available of 1200 kilowatts can supply all 800 kilowatts that stream 5 requires and 400 of the 500 kilowatts that stream 4 requires. And we can use hot utility to provide an additional 100 kilowatts to stream 4. Also, as it turns out, the energy available in streams 2 and 3 exactly match the energy requirement in stream 6. So we can transfer 100 kilowatts from stream 2 and 300 kilowatts from stream 3 to stream 6. And so we find the minimum number of heat exchangers above the pinch is 5. Okay, below the pinch, we have fewer streams and fewer exchangers. Stream 2 can provide 100 kilowatts to stream 6. Stream 3 can also provide 100 kilowatts to stream 6. And stream 3 will have 50 kilowatts left over that can be rejected to the cold utility. So below the pinch, the minimum number of exchangers is 3. In general, when you're determining the minimum number of exchangers, unless there is an exact match between the energy demands of a set of hot and cold streams, the minimum number of heat exchangers above and below the pinch is given by the number of hot streams plus the number of cold streams plus the number of utilities minus 1. In this example, if you refer back to the slide above for the minimum number of heat exchangers above the pinch, in this example, it happens that the heat demand of stream 6 exactly matches the heat available from streams 2 and 3. Therefore, 1 fewer than this number of exchangers is required. So if I go back here above the pinch, number of hot streams plus cold streams plus utilities is 1, 2, 3, 4, 5, 6, 7. Minus 1 is 6. So I would expect that 6 heat exchangers would be required. But as it happens, the demand of stream 6 exactly matches the supply of stream 2 and stream 3. And therefore, 1 fewer heat exchangers than I was expecting is required. Only 5 heat exchangers are required above the pinch. Below the pinch, I have 2 hot streams, 1 cold stream, and 1 utility. That's 4 minus 1 is 3, and that's the expected number. Okay, and you should be aware that the matching performed at this point, again, does not necessarily correspond to the final heat exchanger network design. We'll talk about the heat exchanger network design in the next section here. Okay, to design the heat exchanger network, we consider regions above the pinch and below the pinch separately, and we start at the pinch and move away from the pinch. Directly above the pinch, we match streams so that the flow capacity of the hot stream is less than the flow capacity of the cold stream in order to ensure that the minimum approach temperature is not violated. Okay, we'll see in this example when we look below the pinch, we'll see why this consideration is important. But for now, just recognize that we want the flow above the pinch, we want the flow capacity of the hot stream to be less than the flow capacity of the cold stream. And as we're doing this, as we're designing our heat exchanger network, more than one matching might be possible. For example, in the following figure, either stream 2 or stream 3 can be matched with either stream 5 or stream 6. Okay, so here is the start of the design of our heat exchanger network. Okay, and I have something that looks kind of like the temperature interval diagram here. These are my 6 streams, 1, 2, 3, 4, 5, 6. These are the temperatures that they need to be heated and cooled at. And here I am starting to design my heat exchanger network. Okay, so the numbers inside the circle refer to the heat exchanger number. So heat exchanger 1 in my diagram, again, I'm starting at the pinch. The pinch is at 100 on the hot side and 90 on the cold side. I'm starting at the pinch and working away from the pinch. And my first heat exchanger number 1 is going to connect stream 2 and stream 5. Okay, stream 2 needs to be cooled from 150 to 100. So I'm going to put 150 and 100 here. Then I'm going to calculate the amount of energy that is released when stream 2 is cooled from 150 to 100. Then I'm going to imagine that energy, that's 100 kilowatts. I'm going to imagine that energy transferred over here to stream 5. And then by the first law, I can calculate the temperature of stream 5. Okay, so after passing through heat exchanger 1, stream 5's temperature has increased from 90 to 102.5 degrees. Okay, stream 2 is finished. Stream 2 cooled down from 150 to 100, it's done. Stream 5 has heated from 90 to 102.5. It's not done yet. We need to get it all the way up to 190. We'll work on that later. Okay, then here, heat exchanger number 2 connects stream 3 and stream 6. Got to say all these numbers right. And stream 3 here should be cooled from 200 to 100. When that happens, 300 kilowatts of energy are released. Those are passed over to stream 6, and stream 6 is heated from 90 up to 165. Okay, so stream 3 is also done. And stream X requires some additional energy here. Okay, continuing to move away from the pinch. In this example, the energy available in stream 1 is matched with energy required in streams 4 and 5 in intervals A and B, respectively. And additional energy required for stream 6 is supplied by a hot utility, and temperatures at the outlet and outlet of each heat exchanger. Temperatures at the outlet of each heat exchanger are determined by the energy balance. Okay, so here at step C, I have added heat exchanger 3 and 4. You have to remember the stream. You have to check the stream numbers and the flow capacities by referring to the previous slide. But heat exchanger 4 connects stream 1 with stream 4, and heat exchanger 3 connects stream 1 with stream 5. Okay, and you can check the energy balances. You'll find that this matching results in the streams having the proper temperature. Okay, stream 6 still needs a little bit of additional energy, and so the 5th heat exchanger 5, supplies hot utility to raise the temperature of stream 6 up to the required 190 degrees centigrade. And the amount of hot utility required is 100 kilowatts.
Please,
Yes.
I think there's a question in the chat.
Yes, please.
Okay, the person is asking. So if there's he's asking, can it be a multiple pitch in zone A? And if there's a multiple pitch, how can we deal with it?
Okay, that's a good question, because if you haven't done this for the first time, you might think that it would be possible for there to be multiple pinches. In fact, it's very unlikely. You'd have to construct a very artificial case to have a situation where you have multiple pinches. And this can be seen most easily later when we get to the composite temperature enthalpy diagram, which I believe is on slide 24. When we introduce the composite temperature enthalpy diagram, you can see graphically that in practical cases, it's very unlikely for there to be multiple pinches. It turns out it's not immediately intuitive, but when you see the composite temperature enthalpy diagram, it might be intuitive. For now, maybe just trust me that in practice there's always only one pinch. And when we get to the composite temperature enthalpy diagram, I'll try to provide some insight for why that's the case. Thank you.
All right. Thank you, sir.
Any other questions?
Yes, sir.
Yes.
Okay. Yeah, this is my own questions now. So please, sir. So in case in the system, for example, the outlet of the hot stream, let's say, is maybe 40 degrees, and the inlet of the cold stream is 60 degrees. So that means the temperature, the outlet of the hot stream is lesser than the inlet of the cold stream. So in that case, can we still do the exchange over there or not?
Okay, I gotta. This is a little bit difficult, and it's easy to get confused. Can you repeat those numbers again, or the?
All right. So
example.
Okay, so in the example, like we have only two hot stream. So the outlet of the hot stream is 40 degrees Celsius, 40 degrees Celsius. Outlet temperature of the two hot stream is only 40 degrees Celsius, 40 degrees Celsius.
The example that I just presented?
Not really the example that you just presented. It's another example whereby the temperature of the cold stream is greater than the temperature of the hot stream.
If the temperature of the cold stream is greater than the temperature of the hot stream,
yeah. So
then energy transfer is not possible by the second law of thermodynamics.
Yeah. So in the example, all the hot stream is less than the cold stream. So in that case, that means the question is impossible, or can we do anything about it?
Yes. Okay. Right. Okay. I guess yes. Okay, that's a reasonable question. Yes. If all of the hot streams are colder than all of the cold streams, then you're out of luck.
Out of luck. Okay.
There's no heat integration. There is such a thing as a heat pump, which is a thermomechanical device. It's basically the inverse of a refrigeration cycle. And as the name suggests, a heat pump can transfer energy against the temperature driving force. You can pump energy from a lower temperature up to a higher temperature, but that requires the use of mechanical work in a compressor. And heat pumps are totally beyond the scope of this discussion. And they're also much more complicated and more expensive. So for the purpose of this lecture, we're only going to consider the case where we transfer energy from a higher temperature to a lower temperature. If all of your energy is available at a low temperature and all of your requirement is at a high temperature, then you're out of luck.
All right.
We sometimes speak about heat quality. So energy that's available at a high temperature is said to have a high quality. Energy that's available at a high temperature is very useful. If you have a reactor or something that is producing energy at a high temperature, say 500 centigrade or 700 centigrade, that energy is very valuable. You'll definitely want to recover that. If you have another unit that is producing a lot of energy at, say, 70 degrees centigrade or 60 degrees centigrade, near room temperature, that energy is almost worthless. The quality is very low. because there's almost nothing that you can do with it.
Okay.
So for the purpose of this for the purpose of this example in this lecture, we will only consider the case where we are transferring from a higher temperature to a lower temperature. So the example includes the example is kind of fake and contrived because there's 6 streams and 3 of them are hot streams and 3 of them are cold streams, and they happen to have similar temperatures so that all the heat integration works very well. In practice, in a real design, things aren't always so clean and neat. But for heat integration design, we assume heat transfer only from a higher temperature to a lower temperature, and if that doesn't work, then we don't consider heat recovery. That's a good question.
Yeah, thank you, sir.
Any other questions? Check our poll here.
No question yet.
No questions yet. Okay. Okay, continuing on then now. So that was, now we have designed our heat exchanger network above the pinch. And the next thing, actually, I just checked the time. We're already at 3:25. We started at 2:30 my time, and it's 3:25. Why don't we go ahead and take a break for about 10 minutes? And when we come back, we'll discuss the design of the heat exchanger network below the pinch, and then we'll do the composite temperature enthalpy diagram, and then I'll give students a chance to try this out themselves with the second example. Okay, so we'll take a break for 10 minutes and come back at 3:35 my time, which would be 2:35 your guys' time.
All right, sir. Thank you, sir.
Thank you. Okay, I have 3:35 my time. Can we continue?
Yes, sir. I think we can continue.
Yes, sir. I think we can.
Okay, excellent. Okay, so we are below the pinch now, and we want to match below the pinch. We want to match streams so that the flow capacity of the hot stream is greater than the flow capacity of the cold stream. And in this case, below the pinch, we'll see why this is an important consideration. Okay, in order to ensure that the minimum approach temperature is not violated. Okay, however, in this example, below the pinch, the value of the flow capacity for cold stream 6, which is 4 kilowatts per degree centigrade, is greater than either that of hot stream 2 or hot stream 3. Therefore, if stream 6 is connected directly either to stream 2 or stream 3, an energy balance will predict that the temperature of the two streams will cross, which is impossible. The solution to this problem is to split stream 6 into two streams, each of which has half the flow rate and therefore half the value of the flow capacity. One of these streams is connected to stream 2 and one is connected to stream 3. And then cold utility can provide additional cooling for stream 3. Okay, so on the next slide, we'll try to understand what's happening here. Why is it a problem that stream 6, the cold stream, has a higher flow capacity than either of the hot streams? Okay, so this shows the temperature versus position in a hypothetical countercurrent heat exchanger. Okay, and we're considering stream 2 and stream 6. Okay, stream 6 is the cold stream. It enters at 65, and stream 2 is the hot stream. It enters at 100. Okay, the problem is because the flow capacity of stream 6 is larger than the flow capacity of stream 2, the temperature of stream 6 changes more slowly than the temperature of stream 2. Has a larger flow capacity. It can absorb energy more easily and has a lower temperature change for a given amount of energy being transferred. Okay, because we started at the pinch, the streams here at the right side of the heat exchanger already have the minimum approach temperature, which is 10 centigrade degrees. And because the flow capacity of stream 6 is greater than the flow capacity of stream 2, as we move along the heat exchanger, the temperature driving force, rather than becoming larger and larger as we would like, becomes smaller and smaller, and eventually the streams cross. If I consider only the first law of thermodynamics, only do an energy balance on the two streams, if I want to cool stream 2 from 100 degrees down to 50 degrees, that means that the cold stream will increase in temperature from 65 up to 90, okay, which is impossible because these two lines cross. Okay, that analysis would be consistent with the first law of thermodynamics, but it violates the second law of thermodynamics. I can't have this temperature crossing occurring. So how can I fix this problem? I can fix, so this represents the problem on our heat exchanger design. If I directly connect stream 6, if I directly connect stream 2 with stream 6 using a hypothetical heat exchanger 6, then over here on stream 2, the temperature drops from 100 to 50, releasing 100 kilowatts of energy. If I add 100 kilowatts of energy to stream 6, the temperature, if I want the outlet temperature to be 90 degrees, then the inlet temperature has to be 65, but 65 is greater than 50, so I've had a temperature cross here. Here, this is 100, which is greater than 90, but here is 50, which is less than 65. So directly below the pinch, because the flow capacity of stream 6 is greater than the flow capacity of stream 2, I encounter this temperature crossing. What I want is for the flow capacity of stream 6 to be less than or equal to the flow capacity of stream 2. And I can accomplish that by splitting stream 6 into 2 streams like this. So this part of the diagram here indicates that stream 6 has been split into 2 streams. And now each stream has half the flow rate, half the mass flow rate, and therefore half the flow capacity. And now I can do the heat exchange without encountering a temperature crossing. 100 is less than 90, 100 is greater than 90, 50 is greater than 40, 100 is greater than 90, 66.7 is greater than 40. Okay, so I've split my stream 4 into 2 parts, each with half the flow capacity. Now my heat exchanger 6 connects stream 2 to part of stream 6. Heat exchanger 7 connects stream 3 to part of stream 6. And then I still need a little bit of additional cooling here, 50 kilowatts of additional cooling. So I will include heat exchanger 8, which connects stream 3 to the cold utility. And I can absorb the additional 50 kilowatts of energy to the cold utility. And then my stream 3 will drop all the way down to 50 degrees C. Okay, does that make sense? Anybody want to ask a question about that?
Maybe please, if you can repeat this last part again, it's a little bit confusing more.
Which last part?
This one that is showing. The splitting part.
This issue here about the flow capacity?
Yeah, about how to split, yeah.
Okay, right. So the problem is below the pinch, we want to match stream so that the flow capacity of the hot stream is greater than or equal to the flow capacity of the cold stream. That will avoid this problem of temperature crossing here. The temperature crossing is caused by the fact that this stream 6 has a larger flow capacity, which means the slope is more shallow. The slope is 1 over the flow capacity. So the stream 6 has a shallower slope here. Flow capacity 1 over the flow capacity is smaller. The flow capacity is greater, so 1 over the flow capacity is smaller. And so if I start here and I move in this direction, I'm transferring energy. I'm always trying to transfer energy from the hot stream to the cold stream. But if I start on this side of the diagram here, I have my minimum approach temperature. But as I transfer energy in the heat exchanger, because my cold stream has a flow capacity that's greater than my hot stream is getting colder faster. The hot stream is changing temperature faster than the cold stream is changing. And that because at this point here, I'm right at the pinch. So here I'm just below the pinch. Stream 6 is 90 degrees C, that's at the pinch, and stream 2 is the hot stream, 100 degrees C, that's at the pinch. So right here, I'm right at the pinch. And going this direction is moving away from the pinch. If I start with these 2 streams at the pinch, because the cold stream has a flow capacity greater than the hot stream, as I transfer energy between the streams, the temperature difference between them becomes smaller rather than larger. And so eventually the temperature of the 2 streams crosses, and this, even here, I'm violating my minimum approach temperature because I wanted to have 10 centigrade degree approach temperature. But here, now I'm violating the second law of thermodynamics. Now, past this point, I'm trying to transfer energy in the wrong direction, from the cold stream to the hot stream, which is impossible in a simple heat exchanger. And the cause of the problem is that the flow capacity of stream 6 is greater than the flow capacity of stream 2. Stream 6 is absorbing too much energy. Its temperature is changing too slowly. So to fix that problem, I can split stream 6 into 2 separate streams. I just have a simple T dividing pipe and split stream 6 into 2 streams, each of which has half the flow rate. So the heat capacity of the material in the stream will be the same, but the flow rate in each of my two split streams will be half of the original flow rate. And so the flow capacity will be half of the original flow capacity. Then if I split stream 6 into two, stream 6 by itself has a flow capacity of 4. Half of stream 6 will also have a flow capacity of 2. That means the temperature of the hot stream and the cold stream will change at the same rate as I transfer energy. So I didn't draw the figure, but if I split stream 6 into two streams, then each one has a flow capacity of 2. The flow capacity is the same, so the slope of the line is going to be the same, and the cold stream will not cross here. Okay, so you can hear by the first law of thermodynamics, if we cool stream 2 from 100 to 50, that releases 100 centigrade degrees of energy. But if I add, did I say centigrade degrees? 100 kilowatts, sorry, 100 kilowatts of power. Cooling stream 2 from 100 to 50 releases 100 kilowatts of power. If I transfer 100 kilowatts of power to stream 6, and I want the outlet temperature to be 90, then by energy balance, I can see that the inlet temperature for stream 6 would have to be 65, which is greater than 50. So in this temperature, this heat exchanger 6 here is impossible. The temperatures cross inside the heat exchanger. So that's not going to work. Instead, I can split stream 6 into two streams here. And one of them I will connect with stream 2. So now the total flow capacity here at the top is 4, but the flow capacity on each side here is only 2, which is the same as the flow capacity of stream 2. And so here, everything matches nicely. This temperature drops from 100 to 50, and this temperature rises from 40 to 90. Because these two streams have the same flow capacity, this temperature changes by 50 degrees, this temperature changes by 50 degrees. There's no temperature crossing. The temperature driving force everywhere in the heat exchanger is exactly 10 degrees, and everything is fine. And then here, the flow capacity of stream 3 is 3, I think. Yes, flow capacity of stream 3 is 3. So the flow capacity of the hot stream is greater than the flow capacity of the cold stream, which is what I want. And so I don't experience temperature crossing. The temperature driving force actually gets greater as I go down the heat exchanger. It starts at the minimum approach temperature of 10 between 100 and 90. And as I proceed down the heat exchanger, the temperature driving force gets greater and greater. And here at the other side of the heat exchanger, the temperature driving force now is 26.7 degrees C. Okay, so it's below the pinch, it's okay for the flow capacity of the hot stream to be greater than the flow capacity of the cold stream, but it's not okay for the flow capacity of the cold stream to be greater than the flow capacity of the hot stream. And so that's why I have this requirement here. Okay, does that answer the question?
Yes, sir. It's okay. Thank you, sir.
Okay, you're welcome. Thank you. It's a good question. This is one of the, there's a couple parts here that are kind of difficult and abstract. After you've worked out 5 or 6 examples, you start to feel comfortable with it and everything seems easy and obvious. But the first time you're introduced to it, there's a lot of parts to keep together in your brain all at the same time. So I thank you for asking the question and slowing us down so we take time to talk about it.
Okay.
Okay, so we have arrived at the end, and now we can represent our entire heat exchanger network in a single diagram like this. And now for convenience, I have my hot streams coming down from the top. This is stream 1, stream 2, stream 3. And my cold streams coming across from right to left. This is stream 4, stream 5, stream 6. And this diagram shows all of the heat exchangers. In total, there are 8 heat exchangers, 1, 2, 3, 4, 5, 6, 7, 8. You can refer to this diagram and map it back to the diagrams that were shown on the previous slide and see that this single diagram represents our entire heat exchanger network. So for example, heat exchanger 4 connects stream 1 and stream 4, heats stream 4 from 190 to 290, and it cools stream 1 from 300 to 237.5. Okay, heat exchanger 3 connects stream 1 and stream 5. It raises the temperature of stream 5 from 102.5 to 190, and it cools stream 1 from 237.5 to 150. Okay, I'm not going to go through every single heat exchanger, but that's the idea. And then over here, remember that we split stream 6 into 2 streams. One of them passes through heat exchanger 6, where it absorbs energy from stream 2. And 1/2 passes through heat exchanger 7, where it absorbs energy from stream 3. And then they're combined together at 90, pass through heat exchanger 2, and then this heat exchanger 5 is the hot utility. Okay, everybody okay with that? So this is the answer. If you're taking an exam, this is where you, if you're consulting on a heat integration project, this is the answer. This is what you wanted to develop. You've designed your heat exchanger network. You need 7 heat exchangers, and you can see how much energy is being transferred, and you can use heat exchanger design equations to determine the required heat transfer area for each heat exchanger. Okay, there any questions about this? Okay, if not, there is one more thing to say, and that is to introduce the idea of what is called the grand composite curve. And this will also hopefully answer the question about whether there could be more than one pinch point and what to do if there was more than one pinch point. After you see this diagram, perhaps you will have some intuition about the reason why, in practice, we only ever encounter a single pinch point. Okay, so the entire heat exchange, the entire heat integration problem can also be represented graphically by constructing what we call a composite temperature enthalpy diagram, which is sometimes also called a grand composite curve. Okay, on this diagram, the slope of each line segment has units of degrees centigrade per kilowatt and is equal to 1 over the flow capacity for each interval. Okay, 1 over the flow capacity is the same thing that we plotted here, remember. These lines also have slope of 1 over flow capacity. It shows how much the temperature changes for each unit of energy that's supplied. Okay, but now we're going to construct a diagram like that for the entire heat integration problem. Okay, the diagram shows how the temperature of the hot streams or cold streams rises or falls as energy is transferred between the streams. And adding cold duty using cooling water to remove energy corresponds to moving the cold curve to the right. And as you'll see when we look at the diagram, 50 kilowatts of cold duty are added so that the two curves remain at least 10 centigrade degrees apart at the pinch. Okay, so how are we going to construct this grand composite curve? For each temperature interval, A, B, C, D, I'm going in backwards order here so that we start at the lowest temperature. And I'm going to always start at 0. So at the lowest temperature at the bottom of interval D, I'm going to say that the enthalpy of hot streams is 0 and the cumulative enthalpy is 0. Okay, then at the end of interval D, or in between interval D and C, we add up the flow capacity of the streams that are present in that interval. We multiply by the temperature difference to get the amount of energy. These are the hot streams, so this is the amount of energy that is required in this interval. Okay, so, and this should match the results that we got much earlier. If you look back at the intervals, C, D, 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 these, well, I'm not going to show that. These results are consistent with the data that's shown in the table earlier in the slide in the temperature interval diagrams. Okay, so this is the enthalpy available from the hot streams in each interval, and then the cumulative enthalpy. Okay, and here is the enthalpy required in the cold streams and also the cumulative enthalpy. Okay, so if I add up all the energy available, there's 1.85 megawatts, 1,850 kilowatts of energy are available in hot streams, and 1,900 are required by hot streams. The hot streams can liberate 1,850 kilowatts, and the cold streams require 1,900 kilowatts. Okay, so considering only the first law of thermodynamics, we're in difference by 50 kilowatts. We're going to need to supply at least 50 kilowatts. Okay, but now what I'm going to do is I'm going to plot the temperature versus the cumulative enthalpy for both the hot streams and the cold streams. Okay, so this is my temperature here. I'm going to plot when temperature is 50, Q is going to be, for the hot streams, when temperature is 50, Q is going to be 0. When temperature is 100, Q is going to be 250, and so on. And I'm going to plot the temperature versus the cumulative enthalpy for both the hot streams and the cold streams. And when I do that, the diagram looks like this. This is called the grand composite curve, and the orange line represents the hot streams and the blue line represents the cold streams. And the slope of each line shows how quickly or slowly the temperature changes as energy is added or removed. Okay, so if I take this point here and this point here, if I add this amount of energy to the cold streams, this looks like maybe 750 minus 1400. If I add this amount of energy, the temperature will rise, temperature of my cold streams will rise from 140 to 190 in this region. Okay, my hot streams, this is this is hot streams 1850, this is 1850, and this is 1050. If I add 800 kilowatts of energy, the temperature will rise from 200 to 300. This is interval A for the hot streams. Okay, so, and as we're transferring energy from the hot streams to the cold streams. So the hot streams are getting colder and the cold streams are getting hotter. And adding cold duty shifts my cold composite curve to the right. So by convention, I'll always set the hot composite curve to be 0 at the bottom of the lowest temperature interval. And then as I add cold duty, I'm going to shift the cold composite curve to the right. Okay, here I've added 50 kilowatts of cold duty. And because I did that, because I shifted the cold curve to the right by 50 kilowatts, my pinch point is here. Okay, the pinch point happens between zone D, and this is zone D for hot and cold, and this is zone C for hot and cold. You'll remember the pinch point happens between zone D and zone C. Here is my pinch. Okay, this is the critical point. I need to make sure that the temperature difference between the hot streams and the cold streams at this point is at least 10 degrees C. And in order to do that, I need to shift the blue curve to the right by 50 kilowatts. Okay, if I changed my minimum approach temperature, if I made my minimum approach temperature 15 degrees instead of 10 degrees, then I would have to shift the cold composite curve farther to the right to make sure that this pinch point here was always at least 15 degrees. Excuse me. Okay, so looking at this diagram, perhaps you can develop some intuition about why there's almost always only one pinch point. Okay, you could make up a kind of fake example where this point here also came exactly within 10 centigrade degrees of this point here, but that's very unlikely to occur in practice. Okay, if the slopes of all of these lines are randomly chosen, the probability that the lines would touch at 2 points is very small. Okay, depending on the slopes of the lines, the pinch might happen down here or it might happen up here. But there's probably, in almost all cases, there's going to be a pinch, and in almost all cases, there's only going to be one pinch. Okay, and I can find it by, among other ways, you found it by constructing the temperature interval diagrams and those things, but I can also find it by constructing the grand composite curve and then shifting the cold curve until I reach the pinch, until the minimum approach temperature becomes what I specified as the minimum approach temperature. And then this point is the pinch, and every other point is away from the pinch. So the cold duty is indicated here. The cold duty is the amount of energy, additional energy that I remove. I'm shifting the cold curve to the right by 50 kilowatts. Up here, the difference between this point and this point is my hot duty. Okay, and my hot duty is 100 kilowatts. I need to supply an additional 100 kilowatts to heat my hot stream. Okay, does all of this make sense? Anybody dare to ask a question about this? This is the end. This is the last new idea for heat integration. The rest of the time, we'll just work on an example.
I think we are good. It's okay.
Think you're good. Okay. Perhaps students need some time to sort of digest this idea. So what I would like to do for the rest of our time, I'm going to skip this slide. The slide deals with some details that I don't think are very important. So, and I've actually removed them from the lecture. I don't know. This is an old copy of the lecture notes. We'll skip this slide. And then what I would like to do for the rest of our time is have the students try this example. Okay, I understand that you were given access to the complete set of lecture notes, so you have the solutions to this example available to you, but for the time being, why don't you set them aside? Okay, pretend that you do not have the solutions to this second example and see if you can work it out. Okay, so take out a blank piece of paper and a calculator and see if you can follow the procedure that we have just discussed to design a heat integration network for this problem. Okay, this problem is even a little bit easier than the one that we went through because there are only 4 streams, 2 hot streams and 2 cold streams. Our minimum approach temperature is going to be different. In the second example, the minimum approach temperature is going to be 20 degrees C instead of 10. And in this example, you're asked to do all of the same things. Construct a temperature interval diagram for the process, construct an energy cascade diagram, determine the minimum utility loads, the pinch temperature, then design the minimum utility, minimum number of exchangers network for the process. And if you have time, you can construct the grand composite curve. Plotting the graph would be more convenient if you have access to Excel or something like that, but at least you can collect the data that are shown. You can do these calculations to collect the data that you would plot in order to construct the grand composite curve like this one. Okay, so why don't we pause for about 10 minutes. I have 4:05 here, which makes 3:05 there. why don't we come back together at 3:15, and I will show the first bullet point, the temperature interval diagram, and check if everyone is able to construct the temperature interval diagram, and then see how we're doing. If you finish the temperature interval diagram, certainly go ahead and construct the energy cascade diagram. And we'll come back in 10 minutes and see how everyone is doing. If you think of any questions while you're working on the example, if you think of any questions, please share them with me or the teaching assistant, and I will answer them when we come back together. Okay, so we'll pause for 10 minutes and let you start to work on this example.
Okay, sir.
Okay, sir.
Thank you. I forgot the temperature interval diagram actually takes a fair amount of time. Should we wait 10 more minutes before we show the answer?
Yes, sir. I think so. 10 more minutes.
Okay.
Yeah.
I'll come back in 10 more minutes at 25 after the hour, and we'll show the first part of the answer, the temperature interval diagram.
All right, sir.
Thank you.
Located at interval D and E.
Okay, the question is, how can we conclude that the pinch is between intervals D and E? We'll see it even more explicitly in the next step when we construct the energy cascade diagram, but we can already anticipate the results just by looking at this information here in the rightmost column. So in the rightmost column, I have already tabulated the amount of energy available or required in each zone. So here in interval A, I found that in interval A, I have a surplus of 50 kilowatts. So stream 1 has a flow capacity of 4, temperature drops by 50 degrees. Stream 4 can liberate 4 times 50 degrees is 200 kilowatts of energy. And over here on the right, stream 3 requires, this is also 50 degrees, 50 times 3, 150. Stream 3 requires 150 kilowatts. And so in interval A, there's a surplus of 50 kilowatts. Stream 1 has 50 kilowatts more available than stream 3 requires. So I can pass this 50 down to interval B. Then in interval B, now here the temperature difference is 20 degrees. But in interval B, I have 2 streams that need to be cooled, 2 hot streams that need to be cooled. The combined flow capacity is 4 plus 3, which is 7, times 20 is 140 kilowatts are available. 140 kilowatts of energy are available in hot streams. And over here, I have only 3 times 20 is 60 kilowatts required to heat stream 3 in this zone. So I have a surplus of 80. Okay, so zone A has a surplus of 50, zone B has a surplus of 80. At this point here, I'm doing pretty well. I have 130 kilowatts available. Okay, but moving on in zone C, I won't try to do the math in my mind because I'll probably make a mistake and confuse you. But if you add up the energy that's available over here and the energy that's required over here, you should find that 50 kilowatts more is required over here than is available over here. So zone C is deficient in energy by 50 kilowatts. That's okay so far because we have 130 kilowatts available at higher temperature we can pass down. Okay, but here we used up 50. So now we have 50 plus 80 minus 50. We have 80 kilowatts still available that we can pass down to zone D. But in zone D, we encounter a problem. In zone D, we've lost this stream here that had a whole lot of energy. So in zone D, we only have this smaller stream 2, and both streams 3 and 4 require heating. And so in zone D, I am deficient by 100 kilowatts. Okay, 100 kilowatts is more than I had available to pass down from the higher zone. Okay, so 50 plus 80 minus 50, I had 80 kilowatts here. I can pass 80 kilowatts down, but I'm still short 20 kilowatts. So in zone D, I'm going to have no choice but to supply at least 20. I'm going to supply 20 kilowatts. I'm going to need to supply 20 kilowatts of power from my hot utility to zone D. Okay, so hot utility will enter to zone D. Then in zone E, in fact, there's no streams that need to be heated up. There's only this stream 2 that needs to be cooled down. So I have this extra 60 kilowatts, but I don't have any place to put it. I cannot pass it back up to zone D. That would violate the second law of thermodynamics. I have no choice but to reject this 60 kilowatts to the cooling water. So I can tell from looking at this diagram that heating is going to be required in zone D, and cooling is going to be required in zone E. Therefore, the pinch zone must be between zones D and E here. And that will be confirmed when you construct the energy cascade diagram on the next slide. Does that answer the question?
Yes, sir. Thank you.
Thank you. Any other questions? All good questions. Please don't hesitate to ask. The fundamental concepts are not that complicated, but the first time you work with them, there's a lot of things to keep in mind in order to understand what's going on. So please don't hesitate to ask questions. Okay, are we ready to see the energy cascade diagram, or should we wait another 10 minutes?
I think we can proceed, sir.
Okay. Then using the information from our temperature interval diagram, we can construct our energy cascade diagram. Okay, so in a sense, this is just a summary, a graphical summary of the information that we already collected on the previous slide. But in zone A, as we said, we have a surplus of 50 kilowatts. So we can pass 50 kilowatts from interval A to interval B. Interval B creates an additional surplus of 80 kilowatts. So now we have a total of 130 kilowatts, which we can pass to interval C. Interval C requires 50 kilowatts. So now we have only 80 left. And zone D requires 100 kilowatts, but we only have 80 kilowatts available to pass down. And so we have no choice but to supply 20 kilowatts from the hot utility. Okay, then in zone E, we have a surplus of 60 kilowatts, but we have no place to send it. There's no streams that require heating at such a low temperature. And so we have no choice but to pass this energy to the cold utility. And since we're using the hot utility in zone D and the cold utility in zone E, the pinch must be between zone D and zone E. And therefore, the minimum hot utility is 20 kilowatts. The minimum cold utility is 60 kilowatts. Remember, we said the total net energy requirement for the process was 40 kilowatts based on first law analysis, just adding up all of the energy requirements and all of the energy available, we found there was a surplus of 40 kilowatts. But unfortunately, because of the second law of thermodynamics, we need to supply 20 kilowatts of hot utility, and we end up rejecting a total of 60 kilowatts to the cold utility. Okay, how about our... Okay, so the next thing that we would do, it's not the instructions for this example, skip this step, but we can determine the minimum number of exchangers above and below the pinch. So I'll go ahead and show that result, and then I'll give you a little bit more time to actually design the heat exchange network. So again, at this point, we're not determining the actual matching between hot and cold streams. We're just determining the minimum number of heat exchangers. And above the pinch, we have 2 hot streams, 2 cold streams, and 1 hot utility. 1, 2, 3, 4, 5, minus 1 is 4. We should expect 4 heat exchangers, and that's what we find. We can transfer 420 kilowatts from stream 1 to stream 3, 20 from stream 1 to stream 4, 270 from 2 to 4, 20 from the hot utility to 4, and that makes 4 heat exchangers. 4 arrows is 4 heat exchangers. And below the pinch, there's only one thing to do. We need to transfer 60 kilowatts from stream 2 to the cold utility, and so we'll only require a single heat exchanger below the pinch. Okay, any questions about that?
Sir, I'm confused about
Yes.
the pins above. How do we correlate the one to the 420, 20, 270? Where do we have those numbers?
Okay, the question is how do we get these numbers? This is the amount of energy that's transferred in each heat exchanger. Okay, again, this is, at this point, we're just determining the minimum number of exchangers. This isn't the actual network design. At this point, we only consider the amount of energy that's available in the hot streams and the amount of energy required in the cold streams, and try to find a matching between them. Okay, so we can see above the pinch, we can determine that stream 1 requires 400 watts by going, sorry. From here, we can see above the pinch, so stream 1 is always above the pinch, it never goes below the pinch. Here, stream 1 goes from 300 to 180, that's 120 degrees, times a flow capacity of 4 should be 480 kilowatts. Okay, so stream 1 has 480 kilowatts available to give. Then similarly, stream 2 has 270 kilowatts. Stream 2, remember, we're only going above the pinch, so that's from 250 to 160 is 110. $160 to 250 is 90, times 3 is 270. And proceeding in that way, I can determine the amount of energy required by each stream above the pinch. Then, in fact, there's more than one way of drawing this diagram. There's no reason why it has to be like this. I could transfer some of this energy over here if I wanted. If I can achieve an exact match, if the supply of 2 or more streams exactly matches the demand of one stream, or if the demand of one equivalently, if the demand of one stream demand of 2 streams exactly match the supply of one stream, then I can reduce the number of heat exchangers by 1. But in this case, that turns out not to be the case. There's no 270 plus 20 is 290. There's no stream that requires exactly 290 480 plus 20 is 500. There's no stream that requires exactly 500. So there's no way to reduce the number of heat exchangers below the number that's predicted by adding the number of hot streams and cold streams and hot utilities. So this matching is just kind of preliminary to determine the minimum number of exchangers, not the network design. Does that answer the question?
Yes, thank you.
No problem. Good question. Are there any other questions? Okay, by my clock, we have 19 minutes left. Why don't I give you 9 minutes more to keep working, and we'll come back at 4:50 my time, 3:50 your time, and I'll show the remainder of the results and take any last questions about this. Okay,
Yes,
so we'll come back together at 3:50 your guys' time. Okay, so I believe we're almost out of time for today. So in the interest of time, I will go ahead and show the design and then the composite temperature enthalpy diagram. If you didn't have enough time to finish this, don't worry. This working out such detailed example takes a fair amount of time. So I encourage you to check after class, and you should have the complete set of lecture notes with all of the answers, so you can check your work. Okay, but continuing on. For our heat exchanger network, again, we're going to start at the pinch and work away from the pinch. And we can start by implementing a heat exchanger 1, which connects stream 2 and stream 3. I think this should be 160, not 180. And streams 2 and 3 have these flow capacities. And so you can see that if stream 1 is heated from 180, stream 1 is cooled from 250 to 180, then this should be 160. From 250 to 160, then stream 3 will be heated from 140 to 230. Okay, then moving away from the pinch, heat exchanger 2, we can connect stream 1 and stream 4 by energy balance. If stream 4 is cooled from 210 to 140, then stream 2 should be heated from 180 to 267.5. Then heat exchanger 3 can be our hot utility. Heat exchanger 3 will raise the temperature of stream 3 up to 236.7. And then finally, heat exchanger 4 can connect streams 1 and 3 and cool stream 1 from 300 to 267.5 while it heats stream 3 from 236.7 up to 280. Okay, then lastly, this will require a certain amount of computation. Don't worry if you weren't able to complete all these calculations.
Yes, sir.
Yes.
I would like to ask a question for the previous.
Yes.
For the network diagram.
Yes.
Okay, sir. During the lecture, you mentioned that when the MCP above the pinch, where the MCP is of the host stream, the MCP of the host stream should be lesser than the MCP of the cold stream before we can connect it. But looking at this, for the stream 1 and stream 3, so we see that the stream 3, the MCP is 4, and the stream 3, which is the cold one, the MCP is 3. That means the MCP of the hot stream is greater than the MCP of the cold stream. So that, I think that goes against the rule.
Okay, can you say that again? Again, I want to make sure I don't.
We know that above the pinch, the CP of the cold stream should be lesser than the CP of the hot stream.
Above the pinch, MCP of cold stream should be greater than MCP of hot stream.
Yeah, okay, that is correct. Yeah, the cold one should be greater than the hot stream. But in this case, looking at this example, looking at the stream 3, which is the cold stream, is 3, and the stream 1, which is the hot stream, is 4. So it is inverse. So that means this
one. Stream 1.
Stream 1
up here.
The up. Why we connect the stream 1 and the stream 3? Yeah. So
okay, heat exchanger 4.
Yeah, so the MCP of the stream 1 is 4, which is the hot one, and the MCP of the stream 3, which is the cold, is 3. So that goes against the
okay, right. But we're not right at the pinch here.
All right.
The requirement that the flow capacity of the cold stream be greater than the flow capacity of the hot stream is only for the heat exchanger that is right next to the pinch.
Oh, I see.
Away from the pinch, the difference in temperature could be great enough that even though they're coming together, they still don't cross.
Oh, okay. So wait,
At-
1 minute. Okay.
when you're at the pinch, you're already at the minimum temperature difference. So if you're right at the pinch and you're going in the wrong direction, then you're going to cross.
Oh, okay.
But if you're away from the pinch, you could have a significant temperature. Sorry, my screen is mirrored. You could have a significant temperature difference, and even though they're coming closer together, the temperatures don't cross.
Oh.
So here, the temperature is 300 is greater than 280, and 267.5 is greater than 236.
Oh.
So even though the temperatures are moving together, they're not going to cross.
All right. So
That's a good question.
Yeah, so that means that this law only apply when the heat exchanger is close to the pinch. All right.
It definitely applies when you're at the pinch, when one side of the heat exchanger is already at the minimum.
All right. Okay.
But away from the pinch, you should still check. Make sure for any heat exchanger, it's probably a good idea after you do the first law analysis to check the unknown outlet temperature. It's a good idea to check and make sure that you don't have a temperature cross.
All right. Okay. Thank you, sir.
It's a good question. Thank you. Okay, so we can, using the same procedure that we talked about for our grand composite curve, we can tabulate all of this data for our hot streams and our cold streams. And we can construct our grand composite curve, and our grand composite curve looks like this. And our pinch temperature is not circled on here, but the pinch temperature is going to be here. This is 20 degrees centigrade between 140 and 160. So I need to scoot this over by 60 kilowatts. Is that right? Make sure I say that correctly. Our cold utility, 60 kilowatts. Yes. I need to shift the blue curve to the right by 60 kilowatts in order to maintain this 20 centigrade degree temperature difference. And over here, the difference between these two is 20 centigrade degrees. So 20 kilowatts. So I'm going to need 20 kilowatts of hot utility. And if I add 20 kilowatts of hot utility and 60 kilowatts of cold utility, my process in sum, my process produces an additional 40 kilowatts of energy. But I'm not able to use all of it. I still have to add 20 kilowatts of heat at high temperature and reject 60 kilowatts of heat at low temperature. Okay, by my clock, we have 2 minutes left, which is perhaps time for one short question. Or if not?
Yeah, I think we are good, sir.
Think we're good? Okay. Well, it's been a pleasure. I hope you have learned something. Energy, of course, we're all concerned about global climate change and environmental protection. Energy conservation in manufacturing processes is an important part of that. And in the chemical process industries, saving energy by heat integration is an important concept for students to understand. So I hope you've gotten an introduction from this lecture. It's been a pleasure. I wish you good luck with the rest of the semester.
Hey, thank you very much, Professor Jeff, for
You're welcome.
Great lecture. Yeah, I hope we can meet again next semester.
We'll see. We'll see.
Okay, thank you very much.
Right now. Okay,
Yeah.
I will go ahead and disconnect then in case you need to tell anything to the students. Okay, thank you.
Thank you, sir.
Bye-bye.
Thank you, sir, for the lecture.
Thank you, sir.
Thank you all.
Oke, saya kira sudah selesai semua. Kita bisa meninggalkan ruangan kalau gitu ya. Terima kasih sudah hadir semua.
Okay, sir. Thank you.
Okay, bro. Thank you.
Yo.
Okay, sir. Thank you. Yes, sir.